Hello everyone, we are the Group 21 and the member of our team is the Zhou Yichen, Hao Qi and Yang Tianyue. The project of our is parameter level and module level impact of transformer. Our project has three parts: the introduction, experiment, and the conclusion. First is the introduction. Because our project is meaning of the modifying the transformer, so I will briefly introduce the transformer architecture. The transformer meaning have five parts: the embedding layer, positional, encoding, encoder, decoder, and the linear layer. From the left part of this figure, we could see the encoding layer and the encoder. Because each token of one sentence has no order, so the positional encoding makes order to each token, and the embedding layer encodes the token from the real world to the embedding features, and then the encoder could make correlations of each token, and the decoder is to translate the embedding from the encoder to the decoder, and the linear layer is to predict the future translated sentence, and the function it uses is the softmax, and then is the encoder layer. We could say this figure, and this is the self-attention layer of the encoder layer. We could say the green part and the white part. The white part is the padding token. Why it uses the padding token? Because in the one batch, many sentences has different lengths, and each token uses the padding token to keep the same length of one batch. And in the green part, we could say each token make correlations between themselves, and in the encoder layer, the query key and value are the same. This is the encoder layer. Then is the decoder layer. Decoder layer meaning have two attention layer. First is the self-attention. It is different from the encoder layer. And why it is different? Because in the encoder layer, the translated sentence, it doesn't know what it will translated in the future. So it uses the mask to mask the token behind them, and in the decoder layer, it only makes correlations between the tokens in the front of themselves. And this part is the decoder self-attention, and the second part is the decoder cross-attention. In the cross-attention, the architecture of this part is the same as the encoder layer, and the only difference is the query key value are the different. The query in the decoder cross attention are the decoder the embedding dimension of the token, and the key and value is the embedding token from the encoder layer. This is the only difference. Then we will introduce the experiment of our project.
The experiment part contains three tasks: impact of parameters, impact of different models, and a translation example. We conducted the experiment on two aspects, which are parameter and module levels. For parameter level, we applied changes to the number of heads in multi-head attention, the number of encoder and decoder layers, and DFF, the dimension of feed-forward layer. Due to the limited condition of devices, we simplified the model of attention is all you need by reducing the amount of training dataset. From the result shown in table, we can find that both H and DFF should not be too small or too high, since the final performance will be affected. And increasing N may improve the final performance. N equals to 8 makes the blue highest particularly. Here is the variation on validation laws of different layer norm. We can see that four curves drop dramatically before epoch 10 and become convergent after epoch 35. Significantly, n equals to 8 gives best performance on prediction, and n equals to 2 gives the worst.
And now I will introduce the different performance on different modules. We compare three different parts of transformer, which are layer norm, feed-forward layer, and positional encoding. Firstly, we remove layer norm of attention layer and feed-forward layer of encoder and decoder. We can find that the blue is none, which may be the gradient explored during the training process. From the left table, without positional encoding, performance drops the most, which also reflects the importance of positional encoding. It's necessary to assign positional encoding to each token. The performance of without feed-forward layer has also dropped a bit. We show that feed-forward layer can effectively improve the performance of the model. The right figure reveals the validation loss during training process. Without layer norm becomes not a number after the 10th epoch. The reason may be there is no layer norm, which causes the dimension value to be too large to converge, resulting in the phenomenon of gradient explosion. The validation loss of without feed-forward layer is lower than that of without positional encoding. This is consistent with the result of the left table, which reflects the importance of positional encoding. And there is an example. We utilize the beam search algorithm to generate our translated sentence. The beam search radius of beam search is set to 4. Our model is to translate English to German. Cause we didn't learn German before, we treat Google Translate results as real results. The results of model translation are shown in the table. We use the results of Google Translate as a reference. We can see that the translation 1 is very similar to the real translation, but there are still some differences. We then translate the translation 1 back to English as you can take a bus, with or without GPS dot truth. We found that the model did not accurately translate device, and the word order was reversed because of an extra punctuation mark. We deleted the punctuation marks in translation 1, and the translation result is you can choose a bus with or without GPS. The translation is more accurate. We analyzed the reason maybe the word device was not trained during the model training process. And due to the byte pair encoding method, GPS and dot may often appear together during the training process. So it is regarded as a combined token GPS dot. So an extra dot appears during the translation process.
Then we will make a brief convolution of our project. First, we took an in-depth look at how transform works and the role of each module. And we usually read a lot of papers, and we learn a lot from the paper, just like the attention is all you need. And we read paper, we learn how to learn the transformer, and then we analyze the impact of parameters and modules of a transformer. From the experiment part, we find that the parameter is too large or the too little is not the best, and the parameter keeps the middle of the large and the tiny is the best. And then we learn the module of the transformer. We find that each part of the transformer is really important. And the most important we think is the layer norm, because if we don't have the layer norm, the model can't convergence. And then is the positional encoding, because if we remove the positional encoding, the performance of our model is really not good. And and in the end, we use an example of the translation. We could find that our model can really translate well, and this is all we learned from this project. And in the end, thank you. Very happy to participate in this course. That's all.